Alrighty, so this is the problem. She did the x, t1, and that time 2, 40. Yep, it's 5, 15. And then the next one has to find the average velocity during the same time interval. So let me just add that over here. That way we can see it. Then we go back, then we'll go back. We'll do full screen view. There should be recording. I hope it's recording. Double check. Yes, it's recording. Okay. There we go. Now it shows up. Cool. So I'm gonna erase this top part. I feel like she gave you that kind of to throw you off, and I totally fell for it. If she was gonna give you because I thought it was gonna be like plugging it into the equations, but that's usually for if she asks for it. Probably that for this, because you guys know that that's this displacement equation. I'll see if that's the ability. Okay. So then now we need to find the average velocity. And remember, velocity is the same as delta x over delta t. So then you have your two x's already. So you have your delta x, which you know is 15 meters. Because you just found that. And then you have your delta t, which your first t was 1 second and your second was 2 seconds. So it's 2 seconds, 1 second, right? And then that's going to be 15 meters over seconds. That's 1 second. So then your velocity average is 15 meters per second. Now, if we wanted to get the instantaneous velocity, then you would do the derivative of x, right? So let's see if I can do this like this. Because you're going to have this 2 here come in front, and then minus 1, which is your power rule. And then you're going to get your v. It's like dx over dt is equal to v. Because that just means the derivative of x. Which would be, this one would disappear because this is like t to the 0 power. So it's going to be 0 plus 2 times 5 meters over second squared t. Alright, so this 2 times 5 is the same as 10. Then this t, you can have a second there, and that's going to cancel with the second squared, so the units do lead to meters over seconds, which is what you would expect for velocity. Now, if we wanted to do that into acceleration, let me finish this part. And just so you guys know, I'm using the chalkboard because the marker's kind of dead. I can try using it and see if it'll show up this time. And then to do the acceleration, we assume that there's a 1 here. We're going to multiply it down over here. And you're going to have acceleration is equal to, that's still 0. 1 times 10 meters over second squared. And that t is going to disappear because this is going to be a t to the 0 power equals 1. So then that's going to equal 10 meters over second squared. So that tells you that the cheetah had a constant acceleration because there's no t here, so it's not a function of t. It's just like the straight number. And I'm not sure if she shows that in the key, but we'll go check right now. Yeah, we have 15 meters per second, and then we have 10 meters per second, right? That's this part right here. And then you have your acceleration, which is constant. Cool. That one we're not doing because we just covered that in class. It's not going to be on the quiz. This is another one that was on my quiz when I took the class. Let's see if the mark will show up. If it does, yay. If it doesn't, we'll go back to the report. So this one's really just doing the derivatives of this x. Alright? Because it's going to ask you, given the position of an object, gives you the x variable, derive an expression for velocity and its velocity constant, aka is it a function of time or not? Although counts up there. And then derive for an expression for acceleration and is it constant. And then that part kind of gets cut off at the end. It's just what verifies your solution. There she's usually asking like, do the units check out? Also notice that she says, what role does calculus play in physics? I used to just write Newton created physics to explain, Newton created calculus to explain physics. And she's usually happy with that because she repeats that to us quite often, if you don't recall. So we have x. Yeah, see, it's kind of dead. Can you guys see that x? Oh, kind of. Almost 1.5 meters over seconds to the fourth. Oh, you can't see that at all. Okay, back to the chalk. Incessant wiping of the chalkboard. I swear, I don't know how the cleaning fluids is so not visible. That's good enough. Can you guys even see those ghost marks? You can't really see them. Okay. Is equal to 1.5 meters over seconds to the fourth, seconds to the fourth, t, it's got to be fourth because you want those to cancel out, and it is, plus 2 meters over seconds cubed, t to the third, plus 0.5 t plus 4. Okay. Remember that this 4 is kind of, it's totally standard. This 4 is kind of like a t to the 0. So that 0 is going to come down, and we can multiply it right there. There's no point in subtracting it, it's going to disappear anyway. This t's got a 1, which is going to come down right there, and you subtract by 1. This 3 is going to come down here, and subtracted by 1. This 4 is going to come down here, and subtracted by 1. You know the deal. So then, dx over dt is the same thing as v, which is this power rule that you just did. In case anyone doesn't remember, the power rule is d over dt. I actually don't know the first part of the power rule, but all that matters is the n, which becomes nx to the n minus 1. There's some notation that you do for deriving it, like the dx over dt, but yeah. And then, so then you have 4 times 1.5 meters over seconds fourth, t to the third, that's going to be 3 now. I'm just going to do that. Okay, that's going to become 4 times 1.5. It's going to become 6. That's 3 times 2 meters over seconds third. This is also going to become 6. Thankfully, that one I know off the top of my head, as I should. This one's going to be 1 times 0.5 meters over seconds, t to the 0, and then this one's going to be 0. So right, this t to the 0 is going to become 1. This is going to stay at 0.5 because it's times 1, and then those are 2 6s. So I will write it just so you can see. 6, 3. And then right now I'm writing it, take note that these units do cancel out. If you do the 6 to the third over seconds to the fourth, you're going to end up with meters over seconds. And then the same thing for here. And this one doesn't have a t, but the units is meters per second anyway. So then you're good. And then you take the derivative one more time. And v is not constant. Is a function of t, right? Because it has t variables in there. If those t's change, which it's going to happen because it's time, then your velocity is going to change. And let's take the derivative of this. You're going to do 3. Oh, that's kind of cool. Comes down there, minus 1. Comes down there, minus 1. This one is like a t to the 0. Comes down there. There's no point of tracking it. It's going to disappear. And then you have dv over dt, which is acceleration, which is 3, 6. I changed my notation there. I'm just doing parentheses so you guys can track that I'm multiplying them. Because I know sometimes the dot's hard to see, especially like this. T squared, right? Squared, fourth, that's going to become meters over second squared. Plus 2, 6 meters over seconds cubed. Right, 1 over 3, that's going to become 2 down here. And this one just becomes 0. So then if you write that meter, 2 times 6 is 12. 3 times 6 should be 18. Yes, 18. So then that makes acceleration 18 meters over seconds fourth, t squared, 12 over seconds cubed, t. Cool. And then again, A is not constant. For the same reason as V, it's got those t variables in there, so it's gonna change as time changes. Cool? And then include or verify your solutions or the unit checkout, right? Because I'm just gonna take an example. So for this part here, let's see if I can place it in here. Yeah, meters over seconds to the fourth times seconds cubed. This is going to cancel out. This is going to be left 4 minus 3 goes to 1. Yeah, 1. So then that's going to be left at 1. And then you're going to result in meters over a second, which is the same unit as velocity, and you pull that from the velocity equation, so that's what you wanted to see. If you have extra time on your exam, I will go through each one and show that the units do indeed cancel out. If you're short on time, just say the units are like what we expected to see. Cool. We did that one in class. Let's do that one. Oh, that is dusty. I will not do that again. What time is it? 5:35. Yeah, we've got time for at least 2 more. So, it should be short, yeah. How long does it take a car to cross a 30-meter wide intersection? So, you have a car, you have a 30-meter wide intersection. 30 meters, and then we'll just put the car over here. That's a car. If the car accelerates from rest at a constant 2 meters per second squared. So you know acceleration is constant because they tell you. Acceleration equals 2 meters per second squared. And it's going that way, and we're going to define this as our positive x direction. I'm doing that so that it's not like if this is your positive x direction, then it's accelerating negative. So that direction of acceleration is positive acceleration. That's what she means by define your axes. I put 30 meters, yeah. Cool. So it's asking for t, for time, right? So then for that, you're going to have your kinematic equations. You have a few of them. The most common one is this one. X equals x naught. Let me make sure I do this right. Plus v naught t, and I believe 1 over 2 a t squared. The only thing I'm not certain about is that 1 over 2. Because this has to be a t in order to get you a meters. This has to be squared to cancel out those meters squared from the acceleration. Let me just double check. And yeah, so this one's written like this. This is delta x. All you did here is you moved the x naught over to the side, right? Because delta x would have been x1 minus x naught. And then that would have been on this side. This one would have moved over to this side and become positive because you added it. And then you guys already have yours at home too, or you should. Why am I doing it? You need to see this. Cool. So let's check this out. You have acceleration that's given to you. It's constant, however, so you're not going to input time. You have your initial velocity, which was rest, because it says rest. So from rest is v naught is equal to 0, right? Meters over seconds. So that means, and you can, since you said the axis, you can assume that this is x naught is equal to 0 and v naught is equal to 0. Because the from rest tells you that it's at from 0. So then the only issue is that your acceleration is constant. However, you have to remember, you're plugging into acceleration here. This t is not connected to this a prior to it. So she's actually not really going to give you a non-constant acceleration for the kinematic equations, because then you're going to input t twice. So all it's saying is that acceleration here isn't going to change. So this acceleration value is going to always stay the same. However, it's being used in this expression to describe the distance that gets passed through. So it's okay if the acceleration is constant but still gets a t in this when you're plugging it into the equation, basically. Because you're just plugging it in. It's another value. Why do I keep talking down there? And you're just plugging it in. Cool. So, I'll rewrite this. Yeah. X equals 0. Because this is going to get canceled out. Because it's x naught is 0. And this one's going to get canceled out because v naught is 0. Put a little reminder to x naught. No, that's confusing because then it looks like I'm scoring anybody. Anyway, this was x naught. I'll do it now. It's 0 plus v naught, which is 0. 0t, which is still going to be 0. And then you're going to have 1 over 2a 2 meters over second squared, and then t squared. Right? So now you can simplify this by getting rid of that officially, getting rid of that officially. These two are going to cancel out because they're both 2. So then that equals 1 meters over second squared t squared equals x. So now you're trying to find time, right? And you're wondering what x is. Well, the car's got to cross these 30 meters to cross the intersection, right? So that's your x. You draw an arrow. So that's your x. So then you're going to go 30 meters is equal to 1 meter over second squared t squared. From there, you're going to divide by acceleration, which is 1 meters over second squared, which is going to give you, the way I do these with the units, this one's meters, and then this one's meters over second squared, right? You can imagine that meters is just meters over 1, and then you do these groupings, the small, big brackets, and then that's going to give you meters times second squared over meters. These meters are going to cancel out, right? So then that gives you 30 seconds squared is equal to t2, right? The time's in seconds, and this is a second squared. You got to square root it. Also, you've got a square there, so you got to cancel that out. That doesn't quite cancel it. It technically cancels it out, but it also does things to 30, which I cannot calculate in my head. 30, square root of 30. Square root of 30 is 5.48, which, because I believe she gave you 30 to the third sig fig, yeah. So I'm gonna stay there. Technically, these things have like 2 sig figs at most. So you could do 5.5 and that would technically be correct. She's not gonna really dock points on that, to be honest. Second is time. So that's your answer. Cool. Next one. Do we have time for the next one? We do have time for another one. Alrighty. So these are just a bunch of examples that I pulled from the textbook. They're all from the textbook. Speaking of which, if anyone doesn't have the textbook, email me and I will get it to you. I will not get you the Mastering Pearson because that you have to pay for. It's like different codes and stuff. So let's see, what one of here haven't we done? Okay, so this first one is a lot like the ones we were doing at the beginning, right? That one's actually very simple. You're just gonna plug x2 you're gonna plug in the average velocity equation. So v is equal to the delta x over delta t, that's our average velocity, which is going to be x2 minus x1 over t2 minus t1. In the problem, it gives you that x2 is 8.5 centimeters, and that x1 is 4.3 centimeters. It also gives you T2, I know they're so generous, as 4.5 seconds, and T1 as 2 seconds, right? So that means that the average is going to be 8.5 centimeters minus 4.3 centimeters. Sorry for not keeping my lane straight. 4.5 seconds minus 2 seconds. I'm going to plug that into my calculator because I don't trust my brain in fast math. Minus 4.3. This is going to be, sorry, I have that tendency of like squiggling places. 4.2 centimeters over 2.5 seconds. Great, that's your velocity, but something doesn't look right. Do you guys see it? It's C. C right here. That's not good. It's not in velocity, like, units. Oh my god. So I'm going to go king, hen, died, base unit, buy, drinking, chocolate, milk. Then we're going to go 1, 2. Alrighties. So that's 2 zeros. So we could do this 2 ways. We could get the rest of that and then just move the decimal over twice. Or you could do it the more official way by multiplying it. I'm going to do it both ways. 4.2 centimeters over 2.5 seconds. If you plug that into the calculator, it becomes, I'll calculate it later. And then you have centimeters, which is going to be bigger than meters. Sorry, which is going to be smaller than meters. Meters is bigger, this is going to get the 1. Because you're going to have more centimeters in the meter. You're also going to have the centimeters at the bottom because you need them to cancel out. So you have 2 zeros, you go 1, 1 0, 2 0, and then you have your centimeters there. Because there's more centimeters in a meter than there are meters in a centimeter. People do it with like 10 to the power of negative something. I don't like that. I'm going to do it this way. It doesn't make a difference. And 1 meter. And that's going to get you something that I will calculate right now. So first let's do this part. So 4.2 divided by 2.5. And that's going to get you 1.68 centimeters over seconds. And then again, you move this way, moving that way. So you're going to move this to that way. 2 times. 1, 2. And then you're going to put a 0 there. So it's going to be 0 point, because you just want a decimal point. It's like, you want a 0 before your decimal point, so it's more obvious that it's there. 0.01. That's your 2 movements. And then 68 meters over seconds. And then you do that for up there. But just on top of that, I'm going to divide it by 100. And lo and behold, it also gets me 0.0168 meters over seconds. Cool? So that's one very similar to what we did. And if you're tracking along, it's this one up here. And then the other three, we probably don't have time for all three of them. Yeah, we have like 10 minutes. Car traveling is, that one's a lot like the number 11. That's the 11th in your, that's the 11th in your textbook. That one's a lot like the police car chase that you guys did today. Part moving along the x-axis, that's number 27 I'm talking about. This one. Given by an x equation that apparently copying and pasting didn't do well for. That one's probably going to be deriving it, going from the x, taking the derivative, then taking the derivative of the v. We've done quite a few of those, so I'm not going to pick that one. And then a car slows down uniformly from a speed of 18 meters per second to rest in 5 seconds. How far did it travel in that time? That's like the kinematics equations that we used earlier, right? That's the x equals x naught plus v naught t plus 1/2a t squared. Cool? And then from there, it's as uniformly, so you can kind of assume that there's no acceleration, because it's not speeding up, or like the velocity is not changing so much, if that makes sense. Like it's changing, oh my gosh, I'm not explaining this very well. No, there has to be acceleration. Yeah, there has to be acceleration. We're going to use a different equation. Because if the velocity is changing, then there's acceleration. So then we're going to come look at all of our kinematic equations and be like, which one is going to make like the most sense? So we're not actually given A, but we're given velocity. Let me erase this. We're given the initial and end velocity and the time. So in 5 seconds, so that means that delta t is equal to 5 seconds. And then slows down uniformly from 18 meters per second, so that's going to be v naught, down to rest, which is 0, right? So it's going to be v1. This could be v1, v2. In physics, we usually just do not, which is the same as like the initial starting point. So then you can find the average acceleration. So like the average is delta v over delta t, and that's going to be 0 meters per second, because this is your ending point, minus 18 meters per second, which is your starting point. I swear they turned off the AC. 5 seconds. So that's going to be negative 18 over 5. I'm going to plug that in. Remember that you're going to expect it to be negative because you're slowing down. So it's going to be negative 3.6 meters over a second squared. Right? And I get that second squared from meters over seconds over 1. Because the seconds is the same as seconds over 1. And then combining these two to get me meters over a second squared. I'm chalky. Yeah. So then that gives you your average velocity. Acceleration. And then from there you can plug that one into the kinematics equation, given that your v naught was that. Ideally, you would want like your proper acceleration, but given that you're plugging it into a kinematics equation, you're probably not going to have a function of time as acceleration anyway, especially because we're like first physics. So you can assume that this is very close to your constant velocity, acceleration, your constant acceleration. So then from there, you have x is equal to x naught, which is going to be 0. That looks like a star, which is cute, but not the best one. Okay. Shouldn't be 0, right? Because you're going to set your axis to be that x is 0, because that gets rid of it. Plus b naught, which is 18 meters per second, t, plus 1 over 2 a t squared. With your a, you just calculated there, right? So then you're going to solve for x. This one's going to stay 0. 0. You might as well add it in meters. Plus 18 meters per second. Because you set like this as your x equals to 0, x naught is equal to 0, and this is your x naught. This also means that this is your t0 equals equal to 0. And then this is your t1, which is equal to 5 seconds. Right, so you can plug t in there for 5 is basically what I'm saying. T equals 5 seconds and 0 seconds. And I know we're making assumptions there, but it's going to help you get rid of some variables, or not have to go around so many weird numbers. 5 seconds. Plus 1 over 2. 3.6. 5 seconds squared. Cool. And then we're going to plug that into the calculator. I'll plug it in one by one just so you guys can see a little bit better. This is going to become 90 meters, right? Because these two cancel out. This one stays 0 meters. And then this one is going to become 1 over 2. 3.6. 5 squared. 45 meters, because again, that's going to become meters over seconds squared. So the second squared, because this is a second, and that's a 5. I should make that 5 look better. This is a 5. There we go. And these are going to cancel out and leave you with meters. So then that leaves you with x is equal to whatever 90 plus 45 is. Oh shoot. Oh shoot, you guys never saw any of that. That is my bad. And I will... Hey, well, that's being recorded, so I'll just re-explain it at the end. 90 plus 45. 1, 3, 5 meters. And this is for problem 37. Okay, so I realized I forgot to switch it over on my computer so that you guys can see the screen and all that jazz. I'm going to re-explain right now. So, we started off with the problem. A car slows down uniformly from a speed from 18 meters to rest in 5 seconds. 18 meters, you can assume that's your x naught being equal to 0 since you're setting the axis. You can also assume your t0 starts at 0. T naught starts at 0. So that means your x naught is 0 and your t naught is 0 and your v naught is 18 meters per second. Then you're slowing down to rest at 0 meters per second. Right? So then you're going to need to calculate for, why did I put a naught there? That's x1. And then your t1 is given because it's in 5 seconds. So if you set your x1, x naught as 0, that means that your last t should be 5, right? Because if you do 5 minus 0, that's going to be 5 seconds. And in 5 seconds means within the span, or your delta t is 5 seconds. So let's do a little t2. Nope, because we're using naught. We're using naught. T1 minus t naught Your T naught is 0, your T1 is 5 seconds. From there, you need to find the acceleration. And I'm sorry for maybe messing you guys up at the beginning of this, but you're gonna just use the average acceleration because you're not given it. And second off, this is plugging it into a kinematics equation, and it's like easy, not easy, but introductory physics. So they're not really gonna give you a acceleration that's a function of time for plugging it into a kinematics equation. So that kind of helps in determining what type of equations you're using. Anyway, you're going to find the average acceleration and assume that that's very close or exactly your constant acceleration. So then you're going to have V1 minus V naught. V naught is 18 meters per second. V2 is the rest because you slowed down to rest. And then you have your delta T, which is 5 seconds. That results in negative 3.6 meters per second squared. You're expecting a negative because you're slowing down. From there, this is just showing that, yeah, you can just check out because you had meters over seconds for the velocity and seconds over 1 for the time. And then you combine these two and combine those outer ones and you get meters over second squared. And your units are fine. From there, you're going to plug it into that kinematics equation that you guys usually use. The x equals to x naught plus v naught t plus 1 over 2 at squared. So then your x naught is going to be 0 because you defined it to be 0. Your v naught is what they gave you as your start velocity. Your acceleration is what you calculated now. And your t is those 5 seconds difference. Because, you had t naught is 0 and t1 is 5 seconds. So your t1 is going to be 5 seconds. From there, you just plug it in and calculate. This is just me going, okay, this is 0. This entire thing is 90 meters. Remember, those seconds cancel out. This entire thing is 45 meters because those seconds squared cancel out. That's me showing this right here. Because you add the acceleration units, meters over second squared, times your t squared, which is second squared, and those cancel out to leave you with meters. Add these three numbers up and you get 135 meters, and that is your x. And I am sorry for not switching it over sooner. I think that's out of time. I hope this helped. Feel free to email me, and if you guys don't have the textbook, feel free to email me for that. I can get it to you. So yeah. Cool. Let me scroll through here. If you guys wanted sample 1 problems, then it's not going to be on the quiz, but someone asked me for them, and I didn't get to them last session. So these are some. If you do them and you give them to me, then I'll do them and double check you. These are some of the ones that we did. We did 3, and we did 37. The 11 is all like the police one that you guys did in class today. And then the 27 is a lot of the derivatives that you guys have been doing. We also did this one today. This one we haven't done, but it's the police one from class. This one's a bit lengthy and it was in your book, so I thought someone might have a question on it. That's why I put it in here. That's the solution from the book. This one is also deriving it. I believe we did that one today. And then this is one from your practice, from your files that she has uploaded. And we also did that one today. That one is not yet. So, I think that's it. Let me escape. I hope you guys have a nice weekend.